Hey guys, and welcome. It's Mr. Mustafa here. In this video we're going to learn about differentiation of inverse trigonometric functions. So we are kind of here in this video series in the 9th rule. If you have not watched the previous 8 rules, make sure to check for the link in the description box just below this video. So let us get straight into inverse trigonometric differentiation. So what's the general rule like, right? So general rule, right? So the general rule is if I have to differentiate y is equal to arc sine f of x. Remember, we're going to differentiate the arc sine function first and then differentiate f of x. So we get something like this: y prime is equal to 1 over the square root of 1 minus f of x all squared. So I'm just going to say f squared times f prime, right? In other words, what if I just took y is equal to arc sine x? Then in that case my derivative will just be 1 over the square root of 1 minus x squared. Now you must be wondering what's arc sine and arc cos functions and stuff, right? So these are inverse functions. So inverse trig. Example, if I have the function y is equal to sine x, right? If you have the function y is equal to sine x, I'm just explaining what's an arc sine function quickly. Y is equal to sine x is a function, is a trigonometric function because the vertical line test cuts the graph once only, or is a many to one function. But for the inverse to exist, you can't have many to one function, you need to have one to one functions. Let me just sketch this graph below between the sine graph between -1 and 1. So let me just look at this point and that point over there. To make this function 1 to 1, we need to focus on this block here, right? Let's sort out this block. Right, to make the function 1 to 1, yeah. So that's what we kind of do. So this is that's minus pi, that's minus pi by 2, right? Point is minus pi by 2. Just 1 second, right? So let's see, minus pi by 2, and that's pi by 2, and that's a 1, and that's a -1, right? That's a sine graph. Now a restricted sine graph will have an inverse, right? So I'm kind of restricting this in the domain x is an element from minus pi by 2 to pi by 2, right? So from minus pi by 2 to pi by 2, then this function will have an inverse which we call y is equal to arc sine x, right? So this is the function f, and to find f inverse, what we usually do is we swap the x and the y. So we say x is equal to sine y. Now how do you solve for the angle? We say sine inverse x to solve for the angle, right? That's equal to y. This implies f inverse function is equal to sine inverse x, or is the same thing as saying arc sine x, right? Arc sine x. Now we can see we're getting the point 0, 0, pi by 2 and 1, right? So we can switch these coordinates around, right? And look at, since we are dealing with an inverse function, what does the arc sine x graph look like? Okay, so the arc sine x graph looks like this, right? The coordinates are reversed. This is pi by 2 to minus pi by 2, and this is -1 to 1. That's the x-axis, and that's the y-axis, right? and you can see this is a reflection about the line y is equal to x. So that's the sine graph, right? Arc sine x graph. And similarly you will have an arc cos x graph where you need to make the function 1 to 1, a restricted cos graph, and then arc tan graph. So let me just look at what is the arc cos function. So function f, right, y is equal to arc. Okay, let's look at the function f, which is cos x first, because you need to understand where it's coming from, right? Cos x, again, just quickly, what's the cos graph? You don't need to take everything, just partial functions, the partial graphs of the functions, right? So that's the cos graph. Right, so in order to make the cos graph defined, we just take this block here, just from here we take from 0 to pi, and that's pi by 2, right? That's pi by 2, and that is 0 and 1, and that's minus 1. Now we kind of block this piece here off, right, and let's block it off for you, right? And we can see the function is now 1 to 1, a restricted cos graph. So cos graph, x is an element. For the inverse to exist, we need to say x is an element from 0 to pi, right? And you can see your range is between minus 1 and 1. And for f inverse, we say x is equal to cos y. So y is equal to cos inverse x, or arc cos x. The arc cos x graph looks like this. You see, we're just trying to reverse the coordinates around, just to do it quickly, which is an inverse function. So it was minus 1 and pi, it become pi and minus 1, it become minus 1 and pi. So minus 1 and pi value right there. Then this one is pi by 2 and 0, it becomes 0 and pi by 2. So 0 and pi by 2. And the other one is 0 1, it become 1 0. Oh, so it kind of comes down like this, right? So we got the 3 coordinates sorted. I just need to try to draw the graph, right? That's your cos graph, right? So that's pi by 2, this is 1, that's minus 1, and that's pi on top, the final point there. And that point is pi. Now similarly for y is equal to tan x, so let me just say this is 1, 2 and 3. We didn't find the derivative as in, I'm just explaining what's an inverse function quickly, because we need to look at the restrictions in the graph. Number 3, y is equal to, f is a function y is equal to tan x, right, where x is an element from, we're going to take from minus pi by 2 to pi by 2. So we're going to take from, yeah, so we're going to take from minus pi by 2 to pi by 2, where we get vertical asymptotes. Now on the original tan graph will now become horizontal asymptotes. So this is pi by 2, right, and minus pi by 2 is on the other side, yeah, minus pi by 2. So we have an entire tan graph here, right, so we're going to kind of is a reflection about the line y is equal to x. So the vertical asymptotes now becomes the horizontal asymptotes. So f inverse is x is equal to tan y. Therefore y is equal to tan inverse x, or arc tan x. Alright, so what's the graph for tan inverse x? So tan inverse x graph, obviously you can take some coordinates here and switch them around to get a more accurate graph. You can see the function is already 1 to 1 between this interval from minus pi by 2 to pi by 2. Function is 1 to 1. Horizontal and vertical line test needs to cut the graph once. And so if I'm looking at the arc tan x graph, that's my asymptote. That's my second asymptote here. And that's your arc tan x graph. Right, so that's 0, that's pi by 2 minus pi by 2. If you took an angle like 45 degrees and 1, then you can show it here. Like tan of 45 is pi by 4 is 1. So now you're going to get 1 and pi by 4. So this is 1 and that should give you pi by 4. Yes. Now let us find the derivatives of each of these. Now the derivatives of these three functions are given by implicit differentiation. Now it's not the case that you only get arc sine, arc cos, arc tan. You can also get arc sec. You can also get arc cosec, and you can also get arc cot. But for now, let us focus on arc sine, arc cos, arc tan. So if I take this example over here, y is equal to arc sine x, we're going to find the derivative. How come the derivative is equal to 1 over 1 minus x squared? This is from, we have to end up using implicit here, implicit differentiation. So if you have not watched my video on implicit differentiation, make sure to go back and watch the video. Check for the link in the description box below this video. Alright, so number 3. So let's go back to number 1. So required to prove that, let's prove that d dx of the derivative of sine inverse x is actually equal to the square root 1 over the square root of 1 minus x squared. That's what it's equal to. So let's prove this, and then you'll understand where it's coming from, and then we can apply. So the proof for this is this, and arc cos and arc tan is given in a similar way. So if I want to find the derivative of this function, what we can do is you can say let y be equal to sine inverse x, or arc sine x. So this implies if sine is if y is equal to arc sine x, this implies that sine y is now equal to x. Now we can apply implicit differentiation here. Now how will I draw a triangle for sine y is equal to x? Very important. Now how do I draw a triangle for sine y is equal to x? Let's go and draw a triangle. Let's draw a triangle for sine y is equal to x. Whilst we're here, let us just draw the triangle. Sine of y, so in other words the angle is y, is equal to x. X means opposite hypotenuse. X opposite is x, hypotenuse is 1. So the adjacent will be 1 minus x squared by Pythagoras. We have completed the triangle, which is great. Now if I find the derivative of this, remember we're finding d dx. Now y is already a function in x, so we need to apply implicit. I've also done a video on trigonometric differentiation just before this, which is the 8th one, so make sure to check that out as well. So let's find the derivative of sine y. So derivative of sine y is cos y times y prime, because remember we have to differentiate this. You're kind of finding derivative of sine f of x, so it is cos f of x times f prime x, which is y prime, which is equal to derivative of x is 1. So what do we have? We got y prime is equal to 1 over cos y. Now what do we have? What is cos y? Cos y is from the triangle. Cos of y is adjacent over hypotenuse. So what we have? We have y is equal to 1 over the square root of 1 minus x squared, which is done and perfect. Let's look at the second proof. Let's try to prove. Right, so similarly, we will get a proof. Similarly, right, you can do y is equal to arc cos x, or you can say cos inverse x. To find the derivative of this, we'll get negative 1 over the square root of 1 minus x squared. Right, make sure to get that answer. And similarly for arctan, and if y is equal to tan inverse x or arctan x, y prime is equal to, should get y prime is equal to 1 over 1 plus x squared. That's it. Let me do a difficult one, which is arc cot. Right, so I don't know what the answer is, so let's just say let y be equal to cot inverse x. Right, I want to find the derivative of cot inverse. Let's take this as an example. Right, so we'll take it an example 4, because the previous example was just explaining what was the inverse functions. Right, so example 4, in other words, there's your first example over here. Then looking at example 2, should be able to do this one, number 3 here, and number 4 here. What is the derivative of cot inverse x? Right, cot inverse x, let's say cot y is equal to x. So we'll draw a triangle again. So if we draw a triangle, we know the angle is y. Cot is adjacent over opposite, which is x and 1, and this is the square root of 1 plus x squared. Perfect. So to find the derivative of cot, it is you can look at the trigonometric differentiation that I have done, and I use this table over here, which is sec sec tan, right? Cosec, negative cosec, cot. Derivative of cot is negative cosec squared. So I'm going to write negative cosec squared y times y prime. The derivative of cot y is negative cosec squared y, but remember y is a function in x, so times y prime is equal to 1. Therefore y prime is now equal to 1 over negative cosec squared y. Cosec squared y. Now cosec squared y is opposite, sine is opposite over hypotenuse, so cosec will be hypotenuse over opposite. So square root of 1 plus x squared over 1, and we're squaring that, so negative 1 over 1 plus x squared. So simple. Right, I think we should do one more in number 5. I want to find the derivative of y is equal to find the derivative of sec inverse x. So sec y is equal to x, and draw a triangle quickly. So this is y. Sec is adjacent opposite, sec is cos is adjacent over hypotenuse, so this is hypotenuse over adjacent, x over 1. Yes, and the opposite will now become 1 minus x squared, x squared minus 1. rather should be x squared minus 1. Yes, and then the derivative of sec is sec x sec y tan y times y prime is equal to x. Now what we have y prime is equal to the derivative of x is 1. Right, so we have 1 over sec y times tan y, which is equal to 1 over, what is sec y? Sec y is basically, can we simplify? Yes, what is sec y? It is x. Sec of y is x, and tan y is opposite over adjacent, which is square root of x squared minus 1. So that's what the derivative of sec inverse x is, 1 over x square root of x squared minus 1. I hope you guys are understanding. Don't forget to comment on my video if you are not understanding. Right, so let us look at now, these were just proofs. So how do we go and differentiate functions? Because I started off with something like this. I started off with arc sine f of x. So what do we need to do? How do we differentiate things like that? So let's look at number 6, example number 6. If I have y is equal to arc sine 2x, how do I differentiate arc sine 2x? I'm going to say y prime is equal to, apply the rule directly, 1 over the square root of 1 minus 1 over the square root of 1 minus the argument, which is 2x squared, times the derivative of 2x, which is 2, and that's the final answer. Number 7, if I have to find y is equal to tan inverse x squared minus x, yeah, tan inverse x squared minus x, then y prime will now be equal to 1 over 1 plus this here squared, which is x squared minus x all squared, times the derivative of this, which is 2x minus 1. That's my answer. Number 8, something a little bit more difficult. What if I have to go and find the derivative, y is equal to sine inverse ln 3x squared, right? Then what we'll say is y prime is equal to 1 over the square root of 1 minus ln 3x squared, and kind of need to square this as well, yeah, because the square root of 1 minus this here squared times the derivative of this only, times the derivative of this will be 6x over 3x squared. Unsimplified answer, that's what it is. If you want to simplify, we will get something much more easier. Right, so these are all the possible types of inverse trigonometric. Obviously there are infinitely many examples, and if you do have any exciting example, don't forget to post in the comments. I hope you understand, guys. Thank you.